Great. Thank you so much, Isaac. And thank you to all the organizers of QHack for putting on this great event year after year. I think every year Amazon's participated, it's gotten better. And also thank you to all the attendees for showing up, especially because this event started pretty early on a Thursday. So today I'm going to be talking about some ongoing work we're doing on the Amazon Bracket team, and also kind of an overview of some of the challenges in the field of using near-term quantum devices for quantum chemistry. I'm really grateful that I'm going right after Nathan, who gave such a good introduction to why benchmarking is really important, and also the importance of being realistic about sort of the challenges that are facing our field, where there's a lot of promise for these technologies, but we also have to be honest about sort of what the difficulties we're going to encounter are. So the first thing we're going to talk about is just a quick overview of the variational quantum eigensolver, perhaps for folks who haven't had enough coffee yet this morning or they haven't been exposed to it. We're going to talk about sort of the general way people apply this technique and some of the challenges, and then talk about the project we're doing to benchmark how well some possible solutions to this might help us. So for folks who aren't as familiar, perhaps, with near-term intermediate-scale quantum algorithms, the variational quantum eigensolver, as the name implies, is an algorithm for non-fault-tolerant quantum devices to find low-lying eigenstates, or indeed any eigenstate. There's lots of applications of this, but one arena in which it's very popular is quantum chemistry, because finding the ground state of generic molecules is, in general, a pretty difficult problem, even for classical computers, and there's lots of applications for it. So the general recipe for applying this technique is that we encode some second quantized Hamiltonian of a chemical system as a kind of like digital poly-sentence that we will then run on a quantum computer. We build up an ansatz, which consists of some initial basis state guess in this second quantized occupation basis. And then you apply parameterized excitations to try and improve your ansatz as you go, and you optimize these parameters. And hopefully at the end, you end up with a reasonably good approximation of the chemical ground state. And so there's a bunch of different procedures we'll need to apply here to actually do this. The first one is just even writing down our Hamiltonian. So we start off with the famous many-body Hamiltonian for a chemical system, where you've got both the kinetic energy and the potential energy interactions between all the constituent particles in the molecule. And we have to turn this somehow into a discrete Hamiltonian that we're going to actually execute on some qubits. And so already we have a lot of freedom in how we do this. Generally, the way this is done is that you pick some sort of orthonormal basis of functions in the regular first quantized space, and then you integrate over those to generate an occupation number basis that you can then write for the quantum computer. So this is something that is kind of a well-described process, but even the initial first step of picking those basis state functions gives you a lot of freedom. And then once you've chosen those, you have to figure out how you're going to actually encode this occupation number basis, because the constituent particles we're interested in, electrons or fermions. And so we then have to choose, are we going to encode these using the Jordan-Wigner transform, which is very popular, partly because it's very easy to implement, something a little bit more sophisticated like Bravy-Kitaev, which is more efficient but less easy to implement, or even something more sophisticated like that, like BK Superfast. And then when we start doing our simulation, we have this occupation number basis, but how do we pick our very first initial ansatz? Do we pick something Hartree-Fock style, or maybe post-Hartree-Fock? And which basic functions are we going to pick for that encoding? STO3G, which again is very popular because it's very accessible, but is in general not a particularly good representation of what we think the underlying molecule looks like, or something more sophisticated. So right from the get-go, when we're even encoding these chemical problems for the quantum computer, we have a huge amount of freedom to pick how we're going to try and represent the problem. And that representation choice can have a very large impact on the accuracy and feasibility of our simulation. And then we're going to apply these parameterized operators to our initial ansatz. So which ones? We have to also pick, first of all, is there a maximum number of electrons that are going to be allowed to interact with each other? Are we going to try and exclude some operators based on symmetry? For example, a common version of doing this is saying that you can't move out of a specific spin sector, or you try and say, like, the molecule has some underlying geometry, so I'll exclude any excitation that would violate that constraint. And then, having done all that, we also have to decide which molecules are we even going to try and study, for example, with classical simulation to validate our approach. The whole point of doing this is that we want to find a system where the quantum computer can outperform a classical system, and we also would like to eventually be able to share our results with people, so we need to be able to run the simulation in a reasonable time frame, which often constrains us to running small molecules, even though those are the easiest ones to get right, and not the molecules that we know are going to be challenging for the classical systems we're trying to beat. So it's very common today in the literature. I don't have a very nice survey like Nathan did, but just if you go and read a large number of papers about the variational quantum eigensolver for quantum chemistry, you'll see a lot of choices reoccurring. The Jordan-Wigner encoding, as I mentioned, is extremely popular, partly because it is easy to write down and because many libraries like PennyLane implement it out of the box. It's also quite easy to come up with an initial Hartree-Fock state using these SDO3G orbitals. And it's a reasonable starting point, especially for the small molecules that are tractable to run today, although it's probably not something we should be super confident in scaling up to the really complex molecules we're interested in actually applying these devices for. And then again, for tractability reasons, and of course there are also sort of asymptotic arguments explaining this, we're only going to focus on smaller excitations that involve 1 or 2 electrons, partly, again, because you can make a lot of progress with this, and it's already challenging today, but it might be something that doesn't scale that well when you have hundreds of electrons in the system interacting with each other. Another very common popular choice today is to adaptively add the operators that you've chosen to your ansatz. This is called adapt VQE. And this is also partly done for scaling reasons. And then we also see, of course, that in the literature, most people are studying kind of the same library of very small molecules, like hydrogen change, lithium hydride, or beryllium hydride. And finally, again, to harken back to the great question we had at the end of the previous talk, many of the simulation results in this field are state vector exact simulations, which is great because that allows you to make progress and understand the feasibility of your algorithm. But we know that's not a real effective representation of what the device is going to do. So we've already made, in general, a lot of choices that kind of constrain how well our simulations represent, A, the molecules we want to study, and then B, the devices we hope to study them on. So if you like, we can draw up like a schematic representation of what we're doing here. We start off with, let's say, like an 8-qubit system, and you apply your initial Hartree-Fock state, which I've shown here in purple. Hopefully this renders okay, especially for the stream. And then we use some procedure to start applying excitation operators to it. So for example, here you can pick some operator that would move the state on the 0th qubit to the 5th qubit, which I've represented as Q4 there. And that has some parameter. Then you apply another operator with its own parameter. And through some operator picking procedure, which we'll go into in a little more depth, you can choose operators out of a pool and stack them onto your ansatz and hopefully end up with something that will drive you towards the ground state. And even in this procedure, there's a lot of freedom because you can constrain whether or not you're allowed to pick the same operator twice. And again, are you allowed to violate symmetry? Do you try to pick the operator with what you think is the biggest contribution or operators that don't overlap that together will give a larger contribution than the one with the single greatest one? And there's no sort of theorem that tells you which one is the right answer. The only option you have, kind of similar to machine learning, is to just do it and try. And that requires doing a huge amount of classical simulation and probably writing a bunch of new code that perhaps most people don't have time to do. So I've iteratively built up my excitations to stack on top of my Hartree-Fock state. That's great. Now I have a reasonable guess for what my ansatz should be, and I can start optimizing all the parameters in this and hopefully end up at a reasonable representation of what the ground state is going to be. So easy. The problem with this is that performing this procedure on hardware that's going to be available in the near term is very, very difficult for a couple of different reasons. One big one is that the existing QPUs we have today have very low quantum volume, by which we mean that the amount of gates that they can execute is very limited, especially as the circuit gets deeper, without completely succumbing to noise. So in the little cartoon schematic I drew, you could probably see that the circuit's that are generated in this VQE procedure tend to grow very deep pretty quickly. And there's lots of long-distance 2-qubit gates, which is generally a situation, especially for certain device architectures, that's unfriendly if you're running something in the absence of true fault tolerance. Another issue is that the qubit counts you need can grow very large very quickly, which again constrains the depth of the circuit you're able to execute without just completely succumbing to noise very fast. Then, when we're trying to pick the excitations to add to our circuit, naively, in the most commonly used ansatz, UCCSD, the number of possible operators we can apply grows as n to the 4, so where n is the number of qubits. And the Hamiltonian we're going to use for the chemical system that tells us, how good is this excitation, should I add it or not, and then when you're doing the optimization procedure, that also has n to the 4 terms. So the product of these two things is n to the 8. So the naive scaling of this is polynomial, but 8 is a pretty bad exponent to have in polynomial scaling. It's certainly better than 2 to the n, like for a naive, if you didn't know anything about chemistry and you just tried to simulate every electron in the system. But that doesn't mean it's necessarily going to be feasible, even in a, if you're classically simulating the VQE, let alone on real quantum hardware. So the question we'd like to ask ourselves is there a way we can try and attack this n to the 8 scaling, at least in its most unpleasant parts, and try and drive this stuff down and make it feasible to run either in simulations or real hardware in the near term while we wait for fault-tolerant systems to arise? And that's kind of going to be the focus of a lot of this talk. An additional problem is that the hardware we have today in general is slow and serial. So what I mean by that is if you were trying to run a classical simulation of all this, you could say, well, I'll use an HPC system, which is usually always available, and there's a lot of compute power that you can scale out to. But the quantum hardware, you can't just say, okay, well, I have one trapped ion device, so I'll just spin up 10 more of them and try and run everything in parallel. That's not possible to do. So you really have to be kind of judicious about how you run the final tests of your algorithm on the quantum hardware, which means you have to try and get a lot of insights, A, out of classical simulation, and B, you're very constrained in what you can actually test on the real device. And all of this is compounded by the fact that the devices we have today experience both shot noise and then errors because they're not fault tolerant. And even in the fault tolerant regime, the shot noise issue would still be present. So the upshot is that there's a lot of reason to be excited for using quantum computers to simulate quantum chemistry, but there's a lot of challenges that we're going to have to be honest about and try and overcome while we get there. So there's a lot of sort of hills to climb and valleys to try and get over to try and make this an actual feasible application of quantum computing. So specifically, when we say that the scaling is like n to the 4 for Hamiltonian, what do we mean by that? So these Hamiltonians for the chemical systems, as we showed in the cartoon earlier, are made up of what we might call polysentences, where they're a sum of linear combinations of poly operators, and each element in the sum has some poly weight associated with it. This might be an okay situation to be in if most of those summands had a coefficient that was really small, so they didn't contribute much. Then you could say, okay, well, I'll make an approximation and neglect them. And indeed, this is what, for folks coming from condensed matter or like theoretical chemistry, people have classical techniques that effectively do this, where you try and neglect sort of long-distance contributions that don't affect the final outcome much. Okay. But in many of the encodings we deal with today, especially with the basis set choices we make, we're in a frustrating position where a lot of these words in the sentence all have high contribution weight. So you can't really neglect them without dramatically decreasing the fidelity of your final result to the actual system you're trying to simulate. And as we mentioned, the number of words in the Hamiltonian grows as the 4th power of the qubit count. Which is pretty big, very fast. So for example, for something with like 12 qubits, you could very quickly have several thousand terms in H. And for something with 20 qubits, if you don't have some scheme to try and get rid of these, or try and at least reduce their number, you can soon have 20,000 terms in that Hamiltonian. And if we think, what's the shot throughput rate of a quantum device today? Like, if it's 10 to the minus 3, and you have 20,000 terms in the Hamiltonian, that's just not practical. The device is not up 24/7, so you're quickly going to be running into the fact that the device is recalibrated while you were trying to measure the Hamiltonian, and there's lots of problems with this. And when we're doing the parameter optimization procedure, we have to measure H multiple times, which is pretty frustrating, because there's n to the 4 terms in it. And even if we're using an advanced optimization technique like SPSA, this still means a huge number of measurements at every single training iteration in the procedure. And the problem is even worse if we're using a naive technique to compute the gradient to either make the update or choose operators in the first place. That's where we really hit that end of the 8 scaling. And one might say, okay, well, then I'll just work on finding a better encoding of the underlying Hamiltonian to try and reduce these scaling factors or the qubit count I need, which is a great thing to do. Many people are working on this, but of course, it's not obvious that such a thing even exists. And if it does, it's not necessarily super easy to find. Such a thing may exist out there, but it may take you until fault-tolerant devices exist to come up with it. So what can we do in the near term while we're waiting for both these things to happen to try and make more progress with the tools that we have available with us today? Another way of phrasing this question is how can we extract the useful information from the Hamiltonian in a more effective way? So what we're trying to do is use some information we've encoded in our Hamiltonian to try and A, choose the appropriate operators, and B, make good updates to the parameters we have. So is there a way we can do that that at least doesn't hit this scaling as badly, but still lets us make reasonably good heuristic choices? So there's sort of 2 generic schemes we can apply to do this. These aren't the only 2, but they're 2 that I'm going to talk about today. One is to say, well, I don't want to deal with this Hamiltonian at all if it has such awful scaling, and I'm going to use some easier to measure statistics to pick operators from the excitation pool and apply them to my ansatz. And this is maybe a reasonable thing to do because often in VQE we say, okay, well, I'll compute the gradient of all the operator parameters with respect to H, and whichever operator has the biggest gradient is probably the one that will contribute most to finding the ground state. Now, there's no analytical result that promises that it has to be true. So effectively, what you're computing when you do that sort of step is a heuristic importance measure that you think is a pretty good guide to what the right operator to add is. But it's a heuristic, so maybe you can find a better heuristic. Or perhaps you could find a heuristic to that heuristic that still gives you most of the important information. The issue with this is even if you can pick the operators from the pool very effectively, you still need to do the optimization step, which is, in general, very expensive. So perhaps you'll still continue to use the Hamiltonian, but you'll try and find a way to approximate it. And perhaps one way to think of this is if you can try and find some sort of Hamiltonian-shaped object that still contains most of the essential physics of the Hamiltonian, but without all of the fine detail. Kind of similar to how in machine learning algorithms are often able to identify very JPEG compressed images that don't have a lot of the fine detail, but it's still identifiable to the machine learning algorithm and your eyeballs as a car-shaped thing. And that's enough to tell you and the machine learning algorithm, okay, that's a car and it's not a bicycle. So can we come up with something like this for quantum chemistry Hamiltonians? So there have been a couple techniques developed recently for trying these sorts of things. One option, this isn't, again, the only one, but it's one that we've worked on with our partners at Quantify, is selecting operators from the pool without computing the gradient. So this specifically allows us to avoid running that end of the 8 step to pick operators from the pool to apply to our ansatz. So what we're going to do is compute a heuristic to a heuristic, which is much easier to measure. And effectively, the way this works is this fast VQE algorithm computes only the diagonal components of the Hamiltonian, which it's able to do in one step rather than end of the 8. It's a pretty good scaling reduction. And the claim is this allows you to still capture the essential physics of the problem and select the best operator. If you're interested in reading this paper, it is on arXiv. You can use this QR code if you'd like. And what's nice about this is it's all of these expectation values that are used to compute this heuristic are simultaneously measurable, even in the shots greater than 0 context. And they're able to use classical resources, which of course are cheaper and much more available to do the necessary preparations for this step. And so this allows them to dramatically decrease the scaling for the operator selection, which is great. And this technique is not yet available in PennyLane, but perhaps some enterprising hacker might be interested in trying to apply it. So if you're interested in seeing what the actual results look like, this is from their recent paper and then blog post that they've published in concert with us on the Amazon Bracket team. Again, these are folks from our partners at Quantify, which is a Danish company. So what they've done is they run both classical simulation and then on real hardware, the operator selection step for this adapt VQE algorithm. So they run this fast VQE technique for choosing operators out of the pool on, I think, our simulator, a noise simulator, and then on Rigetti. And then based on those results, they pick the operator and then do the optimization step on a state vector simulator. So the goal here is to kind of show that the operator selection step, at least, you are able to capture the essential information to pick good operators, even in the absence of computing the full end-of-the-8 scaling gradient, which is very important. And what's also rather interesting about this is they found that the presence of noise, at least on the Rigetti device and then the noise simulator, actually often helps them make good operator choices early, perhaps because it gets them out of some bad minimum or something. This is obviously something that I think would be interesting to understand better. So they're able to do a much sort of quicker simulation of choosing these components of the ansatz, but this doesn't yet address the issue of doing the parameter optimization step, which is still a really big barrier for VQE. So the rest of our focus here is going to be looking at various means of approximating the Hamiltonian. So this object, the expectation value of h, given our ansatz, is kind of the essential chunk we need for doing these optimizations. This is effectively computing the forward pass for the optimization if you're coming from a more machine learning background. And we're going to talk about several techniques that have been used to try and do this. And as an analogy, kind of what we're looking to do here is we take several pictures taken with a color filter, and then we use that to reconstruct the full color image. This is like from the early history of color photography. What you would do is you would put like a red, a green, and a blue filter over your camera and take several black and white images, and then reproject with the color filters to try and come up with the full color image. So these images are from the early 20th century. And as you can see, the reconstruction isn't perfect, but it was definitely a very important early step in the development of color film and color photography. And so our goal here is to kind of come up with something analogous for the process of approximating the Hamiltonian's expectation value and hopefully sort of drive the evolution of this whole field in the same way that these early experiments in taking colored pictures did so for the film and photography industry. Okay. So the first technique we're going to talk about is classical shadows tomography. In this sort of a procedure, we take some number t snapshots of each qubit in a basis where each qubit is measured with respect to some operator randomly chosen from the 3 set of polys. And from there, we're able to reconstruct a density matrix for the tth snapshot using a result projector. And the claim is that we can reconstruct the expectation value of the Hamiltonian by averaging over these snapshot density matrices. So you can clearly see that obviously the effectiveness of doing this, unless you guess very lucky the first time, is going to depend on the number of snapshots you take. And this isn't necessarily a free lunch claim that you'll be able to take like some very minimal number of snapshots and perfectly reconstruct the Hamiltonian. Rather, you need to kind of empirically determine what the appropriate t is for your given situation. And you can imagine, for example, taking one snapshot, checking the variance, and continuing that, and sort of asymptotically approaching what you think is a reasonable estimate for this expectation value. So this technique is already implemented in PennyLane. In the VQE context, I have my little pseudocode here. And there's also some really nice demos that are available on the PennyLane website that you can check out if you're interested in this. So all you need to do is build up your ansatz where you start with your Hartree-Fock state. You apply your previously selected excitations and then your new excitation. And finally, you compute the expectation value of h using the shadow exval technique. And the number of snapshots you'll take is determined by the number of shots you pass to the device. So this is really easy to set up in PennyLane, which is awesome. And you can use this to kind of experiment with how well this technique works for either like your gradient computation, if you'd like, or choosing the operator or doing the optimization step. Another technique that is also available in PennyLane, which is awesome, is trying to group the Hamiltonian into what are called qubit-wise commuting polys. Oh. So the way this works is that we said we had like n to the 4 of these poly strings or poly words, and we'd like to find groups of them that can be measured simultaneously. So if, for example, we have a poly that's Z's on qubits 1 to 5 and X's on qubits 6 to 10, those are simultaneously measurable because they don't contain any polys on the same qubit that are not simultaneously measurable. So using algorithms from graph theory that are designed for what's called clique finding, you can reduce the total number of measurements you need to make to exactly compute the expectation value of H by a very large amount. Up to 90% in some cases. So that's great. The issue, of course, is that if the total scaling of the number of terms is n to the 4, where n is the number of qubits, let's say if n is 10, that means there might be 10,000 elements in H, so reducing it by 90% is awesome, but it still means there's 1,000 terms in this you have to measure, which can be quite a lot. And so the number of non-commuting groups will still grow quite quickly if you're using this qubit-wise polyword strategy, even though the reduction you see is obviously very helpful. And again, this is very easy to implement in PennyLane. There's great support already for computing what's called the grouping of a Hamiltonian. You generate some Hamiltonian, let's say, and then you can just apply this QWC or qubit-wise commuting grouping to it. And then you can simply measure the expectation value as you normally would, or in fact, what PennyLane does internally is it will compute the separate 1,000 expectation values for each commuting group and then combine them at the end to give you the result. And that happens behind the scenes, and it's pretty nice and convenient. So then one might ask, these two techniques seem great. You're able to reduce the number of shots you need, and you're able to use a lot fewer sort of groups in general. Can these be combined? So recently, as in the last year, there's been some work on using so-called shadow-informed grouping, or in this case, I've called it colorful shadows. And this is kind of analogous to the color photography example I showed in the beginning of this section, where what we'd like to do is combine grouping with classical shadows. And the idea here is that you can prove actually that this is able to measure these so-called poly words or phrases very effectively. Again, this technique is also not implemented in PennyLane yet, but perhaps an enterprising hacker might be interested in trying this. And if you're interested in reading the paper, again, it's available at this QR code. So in this situation, we've got 6 poly phrases on 4 qubits, and I'll explain what the colors are. So these coefficients here are in ascending order. So this poly phrase at the top has the highest weight, and then C2 here has lower weight. And I probably should not have the microphone next to the speaker. That's a little dicey. Oh, shoot.
Yeah, you gotta stand away from the projector.
Sorry. OK, there it is. It's back. All right, lesson learned. C4 has lower weight than C3, and C5 lower, and C6 lower. OK. And then as we move right in the table, those are the 4 qubits. So an empty box means it's just the identity. Green is one of the polys, purple is another, and pink is the third. It's not particularly important which one each one is. It's just they're 3 distinct polys. So if I give you some poly chunk like this, or a poly phrase, can you find an efficient shadow scheme to approximate this thing? And if so, how do you do it? So the paper argues effectively what you should do is you compute an overall weight for each option on each qubit, and they give a scheme for doing this in the paper, which I won't go through here, but you're welcome to read it. And then you descend in decreasing level of weight through this poly phrase and allocate which measurement you're going to make on each qubit. So in this case, the top line has the highest weight, so we'll pick whatever the green poly is on qubit 2 and the purple one on qubit 3. Or sorry, qubit 1 and qubit 3. Then we go down the next one in the table, and we see that on qubit 3, everything's fine. There's just an identity, so we'll measure that one again. And then on qubit 1, there's a conflict. We could stick with the green, or we could go with the pink. But our weight formula says that the green one has higher weight, so we should go with that. So we're choosing here to make an approximation where we say green and pink are not simultaneously measurable, but the contribution of green is more important, so I'll approximate with that. Then at the next level, we stuck with green again because there's just some identities. We add a new purple in because we encountered one of those on qubit 2 in this sort of third row. We keep proceeding, we hit another green, that's great. So if we'd encountered another pink here, we would need to see now if the total weight of the pinks from 2 and 4 overwhelmed the weight from 1, but luckily we didn't encounter that situation. If you do, there's a formula for figuring out which one to pick. But effectively, what you'd like to do is bias towards the one with the highest contribution to the overall phrase sum. Then we keep advancing down the list of qubits. So we see now there's a pink one on qubit 0, and there's still green on 1, purple on 2 and 3, and then finally, in the last row, we hit another pink, but I've kind of cheated here and said again that the pink is lower weight, and it's low enough that the weight of the greens overwhelms it. So now we have a scheme for measuring on all 4 qubits, some final measurement protocol. So we compute the expectation value with respect to this, and we use that to approximate the weight of all of the summands in this chunk. And this paper, again, gives like a more developed scheme for how you pick these phrases and then how you just make the sort of decision from weight to weight. But this is a provably more effective way of combining both the qubit-wise commuting scheme and then also the classical shadows technique in kind of a group-aware way. And so the goal here is to allow us to approximate these Hamiltonian expectation values more efficiently. Cool. And then the last technique I'll talk about, which I didn't make any attractive tables for, which I'm sorry for, is using positive operator valued measurements to do tomography similar to classical shadows. So this technique is a little different because the previous 2 we looked at, both the qubit-wise commuting and the shadows, have us using exactly the number of qubits we started out with that we were given. This technique is a bit different, where what we say instead is we'll add a new qubit array of ancillas, and we'll pair each ancilla with the one original measurement qubit in my original VQE problem. So effectively, we've doubled the number of qubits we need, but that might be worth it if we can effectively simulate the Hamiltonian thanks to doing this. So the way this scheme works is we construct a positive operator valued measurement. And again, if you're not familiar with that, totally fine. Check out the paper link here, which involves entangling each of the measurement qubits with an ancilla through a unitary U, which is a linear combination of 2 qubit polys. And this instantly generates for us 8 trainable free parameters for each measurement qubit. And our goal is to adaptively tune the number of shots and the number of parameters, and the parameter values to approximate H for whatever initial wave function we put in. So for each qubit, we've got these 8 trainable free real parameters, and we go shot by shot, making updates to them using whatever update scheme you want to use. And then when we end up with the trained free real parameters that we think give us a good approximation of the Hamiltonian, we're able to use those to much more efficiently measure the final state as we perform the VQE procedure. And we can also compute easily the variance of the expectation value of H that tells us, you know, I've added enough operators to my VQE ansatz that is drifted from the initial one I used to train these parameters. So I need to do some update parameters to my Hamiltonian approximation scheme and then restart the VQE procedure. And the claim here is that doing this allows us to use fewer shots total dramatically than doing something like qubit-wise commuting or naive classical shadows. So effectively what we're trading off here is having more qubits that we need to simulate or more qubits that we need in the real device, but we're going to be able to get away with far fewer shots. So if you have those more qubits available, that's awesome. If not, you may need to try and figure out some other way to approach this issue. So finally, I'm going to talk about an ongoing project that I'm working on at my work at Bracket, which unfortunately I don't have a lot of data to show yet, but it's kind of ongoing in the spirit of seeing which of these techniques is most effective in which situation. Like I've outlined a whole library of techniques, which is awesome, but which one is good? Like which should you use when? If you use these, will your thing still not be feasible to run on a quantum computer or not? How would you know? So our goal is to do a bunch of classical benchmarking using various techniques to try and make things most favorable to what the actual quantum computer would do, and see which of these techniques is most viable in which situation, which should you use with certain molecules, and with certain encodings. So we're studying this using this Tetris Adapt VQE, which is an update of naive Adapt VQE to try and generate shallower circuits. And we're studying, just for now, even the simple molecules I outlined earlier, the hydrogen chains, lithium hydride, beryllium hydride, partly because it's kind of similar for anyone with a condensed matter background. If you can't get the Ising model right, you're not going to get anything else right. And if you can't get MNIST in image classification, you're probably not going to get any more complicated problem. So if you can't handle these molecules to some degree of accuracy, you're probably sunk for more complicated systems like benzene or CO2 or anything with a more complicated metallic atom in it. And we're also interested in running this both at finite shots and with and without kind of realistic or device-inspired noise. Again, because what we would like to do is generate some guidance of when will this be useful on a real device, or what properties would the device need to have for this to be feasible to run on it. And we're also looking at various techniques for doing the optimization and gradient selection, for example, using SPSA. How much of a benefit does it give you over parameter shift, or is the accuracy loss too bad? Looking at things like the different encodings I talked about, things like the Brodby-Kitaev encoding can allow you to use fewer qubits. Is that enough to make some of these approximation techniques more or less feasible? And finally, of course, we would eventually like to run some of this on real hardware, which is kind of the real acid test of this. You can do 1 million simulations, of course, but the real test is whether your technique succeeds on real hardware. So effectively, what we would like to do is generate kind of like a recipe book or a charge table for these kind of VQEs. Are they feasible? In what cases? What techniques do you need to use? Or what parameters do the devices need to achieve for this to be feasible in the NISQ era? So some open questions for this problem is whether you're going to be able to get away with using things like error mitigation, or are we really going to need fault tolerance? Are we going to be able to do any of this in the NISQ era, or do we just have to wait for real error-corrected devices? And how much does any of this extend to larger molecules? Part of the problem, of course, of focusing mostly on smaller molecules is that the very fact that they're easy to simulate can bias you in which technique you choose. Again, similar to the Ising model, where you have to get these right to have confidence in your technique, but getting them right, of course, doesn't mean it generalizes to systems with more complicated interactions. And then we're also interested, as I mentioned, in looking at these sort of hyperparameter algorithm choices of what's the best way to compute our gradients, to do our optimizations, which hyperparameters should we choose for the optimizer? Can we account for things like the real-world drift in the devices, when they go down overnight? Accounting for things like the actual chip topology when we choose the operators we want to include in our ansatz. Lots of other choices we can make. And then also looking at some of these new importance measures that aren't based on gradients. So one thing you might have noticed in this whole talk is that VQE, of course, like many people say, it's one of the more promising algorithms for near-term quantum computation, but it's such a huge family of techniques with so many possible hyperparameter choices or algorithm choices that we really need more clarity and more confidence about recommendations of what specifically to do. Because there's so many varieties of VQE, you could spend the rest of your life benchmarking it, which might be like an entertaining way to spend your time while you wait for fault-tolerant devices, if you like doing HPC workloads. But if you want to run something on real quantum hardware in the relatively near term, you need to quickly develop some kind of opinion about these various questions. So that's part of what I'm hoping to do with these simulations. And so kind of to sum up this segment of the talk, we'd like to stock our toolbox with effective tools for what we want to do. So we don't want to be doing the equivalent of trying to hammer nails with the back of a screwdriver. That's silly. And similarly, we don't want to be using the wrong algorithm or approximation technique for the system we're trying to study. And we don't have a lot of clarity necessarily about the best tools to use. It's kind of a similar situation to Nathan's great talk about the ML algorithms, where there's a lot of published materials about various techniques, but there hasn't been a lot of cross-comparison between them, partly because a lot of people, it's very hard to get other people's code to run. There's not a lot of incentive to do that comparison necessarily if you're trying to publish things. But this is something we really need to do to understand what these devices are going to be useful for and when. And this is a great opportunity for things like PennyLane that can help us with coming up quickly with tests for things like HPC simulations. And so finally, what we're going to talk about is how PennyLane and then the code I work on in Bracket can make it easy to set up these kind of simulations, run them, and transition to running on real quantum devices. So, as I said on the title slide, I am an applied scientist at Amazon Bracket. We're one of the sponsors for QHack 2024. You can see us with the AWS logo right there. We're also providing credits and power-ups for the sort of longer-term hackathon, so stay tuned for that. So if you've never heard of Amazon Bracket before, I'll give a quick intro. It's our quantum computing service at AWS. It's fully managed, and it lets everybody from scientists to newcomers to the field to explore quantum computing. So you can build circuits or experiments using our SDK or third-party integrations like PennyLane. You can test it with simulators that we provide on our service, and then you're able to run on real quantum hardware using the same scripts you used in the build and test stages. And finally, you're able to analyze your results using a bunch of the convenience features that we offer. And so using PennyLane with Bracket is really, at least for me, very useful because I'm able to start with the pre-built templates and data sets for quantum chemistry that the PennyLane folks have worked really hard to build. Of course, they have many templates and data sets for other things, but since I'm working on chemistry right now, these are the ones I'm focused on. And using the integration with Bracket, you can go very quickly from a high-performance simulation to running on a quantum device. And it's now even easier to do this now that we've launched a remote decorator feature that allows you to take your script that you tested out in a notebook and run as a high-powered experiment or simulation using our hybrid jobs feature. You'll hear more about that during some of the later Bracket presentations. And you can use PennyLane's awesome high-performance simulators in jobs as embedded simulators or get priority access to the QPU when you use a job. And at QHack, as I mentioned, we'll be hosting office hours on Discord, so whether you're in person or remote, check us out there. And we'll also be providing power-ups during the hackathon at various stages, which again, you're going to hear more about. Probably of interest to many of you is that we do provide access to various quantum computers. So here are the 4 QHPs that are available on Bracket right now. And in particular, I just want to call out for hackathon participants, especially if you get credits, OQC, Oxford Quantum Circuits Lucy device is going to have extended availability. And we also are offering QEra's device, their analog Hamiltonian simulator Aquila during the hackathon. So if you're interested in using either of these real quantum devices, either come talk to me after the talk or any of the Bracket people who will be on the Discord. And finally, in the interest of not going too long over time, I'll just say thanks to everybody who's attended. Thank you to Xanadu again for organizing this awesome event year after year. If you're interested in using Bracket or using any of our devices during the hackathon, come to the Bracket workshop on Friday the 16th, and the PennyLane demo with Bracket also on Friday the 16th with my coworkers. And if you want to learn more about Bracket in general, feel free to grab any of these QR codes. And with that, thanks again, and I think we're good for questions.
Yeah, awesome. Thanks, Katie. Yeah, Guillermo, we can get to some questions. One thing that I noticed in your talk, this is super, super random, but I'm a condensed matter person. You pronounced Ising correctly. I never do that. It's easing. Fun fact. Yeah, Guillermo, anybody who wants to ask Katie a question, feel free to do so. We'll hand a mic over to you. Yeah, question in the front there.
Hi, Katharine. Thanks for the nice talk. In the first half of your talk, you spoke about reducing the measurement overhead. I have a slightly different question on that note. So, actually 2. One, when you showed us the results from your quantum computer, what was the fidelity of your gates? And 2, have you analyzed what actually happens, when with the noisy gates? How does the error scale with the probability of noise in quantum gates? And supposing supposing no spam errors, then what happens?
Yeah, so it's a great question. I think you're speaking about the data from Quantify. So let me just go back and pull this up. This is kind of a hybrid run that they did where they do the selection step with the quantum computer, but the actual optimization, which is the one that's in some effect most vulnerable to noise, is done on the simulator. So they prepare, they have their ansatz that they prepare and then run on the quantum computer for the selection step. And they discuss in their paper how they exactly construct this. But then for the optimization, since it is pure state vector, the issue that you bring up of the compounding noise is somewhat less relevant. It is during the operator selection step because the ansatz grows at each step, so the circuit you're running becomes deeper. And then to the question about 2-qubit fidelities, so as you can see here, they ran this on Rigetti's Aspen M3. Off the top of my head, I don't remember exactly what the mean 2Q was, but I think we do have that data historically. You could look it up. Having not run on Aspen M3 myself super recently, I don't want to like say anything too specific about the device's performance, when they ran this. But my understanding too is that because Rigetti's device is superconducting, the 2-qubit fidelities can vary like quite a bit between the different Qs. So I think that they were using the whatever tooling Rigetti provides to come up with like the most efficient mapping. But since I didn't run these simulations myself, I don't want to say anything too strong about what they did or didn't do. But I think they do include a lot more details of how they actually ran this in their paper, which is available this QR code. Yeah.
One quick question. So, in this graph, was any error mitigation used?
I don't think so.
Okay.
Yeah.
Okay, any more questions for Katie in the audience here? Okay, if not, we have one question in the chat from Andresu Lead. I think this person's been at QHack before, actually, so welcome back.
Welcome back, yeah.
So maybe a bit more broad, but among the methods you've mentioned, which there were quite a few, which has proven to be more effective, or do each of them possess distinct advantages and disadvantages?
Yeah, it is a good question. I mean, to answer the first point, which is most effective, that's exactly what our benchmarking project hopes to find out. Or maybe a better way to say it, I think, is like which is most effective in which situation. One, of course, you can't rule out the possibility that one just blows all the others out of the water, but I strongly suspect it's going to be one of these, like in this situation, you should do this, and in this other one, you should do this other thing. And then, yeah, I think that each one kind of does sort of have advantages and disadvantages. For example, with some of these like POVM schemes, you do need double the number of qubits for this ancilla entanglement procedure, which is great if you have that many qubits. But if you don't, it really limits the size of problem you can simulate, or you have to constrain the number of electrons you want to run with, which might affect the accuracy of your results. And then for some of the others, like and this is also in some ways true of like some of these adaptive shadow techniques or like the adaptive POVM techniques, you have to sort of like run shot after shot after shot, hoping you converge, and hoping that the variance of your expectation value goes down, but you're not necessarily given a guarantee of when that happens, and it could take a very long time. So you aren't necessarily able to say like with confidence going in, like I know how many shots I'm going to need to be able to converge this. Versus with some of the qubit-wise commuting techniques, you can say, once I've partitioned this into the groups, I'm comfortable just running like a certain number of shots for each one, so I'm guaranteed that I'll use maximum this many, and I will be able to finish the run by the time the device goes down, for example. And then in the shadow grouping technique that I talked about with my colors that I spent some time drawing. One advantage of this, I didn't pull out the entire proof, but they do have upper bound on the error that's induced by doing this versus just using straight up qubit-wise commuting, which it's always helpful if you have like an actual proof that the error is maximum some number. Then at least you can kind of account for that in the rest of the simulation by, for example, running more shots or making your phrases smaller, things like that. So at least then you're aware kind of what you're trading off in each scenario. So, yeah.
All right. Any more questions for Katie in the audience here? No? All good? Okay, well, one more round of applause for Katie. Thanks so much for joining us again at QHack.